a huge task for us whenever we are dealing with electric fields is how in the heck do we calculate an electric field? Now, it's simple to calculate the electric field for a point charge in space. The electric field for a point charge in space, we've shown from Coulomb's law, is equal to the value of the source charge, or it's directly proportional to the source charge and inversely proportional to the distance squared from the source charge. And we know for those point charges, the electric field is spherically symmetric. What that means is if there's a sphere drawn anywhere around that source charge that is centered on the source charge, then the electric field everywhere on that sphere will look the same. So it's really easy. Oh, and I forgot my r hat vector here. R hat is just a unit vector that is pointing away from the source charge. So calculating electric fields for point charges is really easy. What's not so easy, as we've seen before, is calculating the electric field due to a line of charge. So due to a line of charge, we could certainly do the prescription that we've done before. We could say we have a y-axis, we have an x-axis. We can break this charge up into tiny little pieces. Let's say this charge has a total amount of q. This element is dq. This is going to have a tiny electric field dE. And you also know that there is a mirror charge on the other side contributing to a tiny electric field dE. And then you have to do some integration. You could use symmetry to cancel out the horizontal component, and we're going to be left with the vertical component to the electric field. Okay, so we've done that, and we know obviously this is a lot of work because almost any time you use calculus to set up an integration for charges, those calculations can often be tedious. Now, here's the power of Gauss's law. If our charge configuration has a certain type of symmetry, then the electric field surrounding that charge configuration will match the symmetry. Now, for a finite line of charge, and I'm going to draw a little image down here. I'm not drawing on a nice surface, so my lines are coming out a little funky. So if we had like a small charge there, well, a point out in space over here for that small charge would have an electric field that is pointing out like that. And a point over here for this small charge would have an electric field pointing out. Point here, electric field pointing out. And I'm assuming that this charge is a positive charge. That's how I know the electric field is pointing out. The electric field will probably look more like this. The further from the ends we are from that charge, and then as we get closer to the ends again, the electric field will alter in space. So the electric field will definitely have a horizontal component if we are close to the ends. But a lot of times we are interested in a region in space that's not close to the ends, but rather, and let me just pause for really quickly. Because I have everything kind of on this one little screen, I'm not able to be at my multiple screen setup. It may be hard for me to see if you put a question in a chat. So make sure that if you have a question and I miss it in the chat, make sure that you just yell out, say, Mel, I have a question. And that way I can make sure that I could address your question. Also, be careful because since I only have this one screen, if you have a private question, everyone will see it. Oh, hold on. Let me rephrase that. Maybe I could change the settings so you only see this one screen. That'll be better. I forgot about that. Okay, so hypothetically now, if you have a private chat, hypothetically, only I would see it, but just a heads up. Okay, so back to the electric field. Now you see what I've drawn here, and actually let me do some things with this. I'm gonna just want to center this a little bit more. So what I've drawn here is an electric field, and this is not a uniform electric field. This electric field is not symmetric. And the reason why it's not symmetric, at least it's not symmetric to a type of symmetry that I'm going to call cylindrical symmetry. And the reason why, if I create a cylinder, let's say around, oops, wrong mode. If I create a cylinder, that's a bent cylinder. If I create a cylinder, the electric field does not look the same everywhere on that cylinder. So that finite line of charge doesn't have cylindrical symmetry, at least, nor does it have spherical symmetry, nor does it have a box symmetry. It might have a symmetry of another type of shape, but not any of those common shapes that we know how to deal with. Unless we're at a point kind of far from the ends. Now, if we're at a point kind of far from the ends, then relative to that point, let's draw a cylinder now. So relative to that point, the electric field looks the same everywhere on that side surface. And if we look at the left end of the cylinder, so there's a left end here, the electric field looks the same everywhere on that left cap. And if we look at the right cap, the electric field looks the same everywhere on that right cap. So if we're far from the ends, this cylinder has cylindrical symmetry. The electric field looks the same. And why that is important to you, it's because if we're interested in the electric field due to, let's say, a line of charge, and we're not close to the ends of the charge, if we're some distance away from the ends of the charge, then that electric field has cylindrical symmetry. And by having cylindrical symmetry, what that means is we could use Gauss's law, not because it has symmetry, but we'll want to use Gauss's law because it makes calculations simpler. In using Gauss's law relates the electric flux of a closed surface. So this circle through this integral means the surface is completely closed. So if I just draw a cylinder, that means this cylinder could hold, let's say, water, because it has a left end, it has a right end, and it has a side. So this cylinder can hold something. It separates a region of space inside the cylinder from a region of space outside the cylinder. So that's what this circle in the middle of the integral means. It means we have a closed surface. Now, Gauss's law is a surface integral, which means it's the dot product between a vector and some surface area differential. So that surface area differential can be broken up into the number of different sides you have if you want. So here for the cylinder, we have 3 sides. So I could just express this integral as 3 integrals over the 3 sides. So an integral of the electric field over the left side. So that area differential is perpendicular to that left side, and that is a vector. Then we can, and let me put an equal sign here, not a plus. And then we have the integral of the electric field on the right side dotted with the area differential from the right side. So that would look something like this. Area differentials are perpendicular to the surface that they represent. And then we have area differential on the side, and this would be a plus the dot product of the electric field on the side and the area differential on the side. And what Gauss's law says is it says if our surface completely encloses a volume of space, when you sum up all of those surface integrals, it's equal to the amount of charge that is inside that volume of space, the amount of charge contained in that space. That's why we call this Q enclosed, divided by epsilon naught. Gauss's law can be used for any shape. It doesn't have to be a cylinder. It doesn't have to be a sphere. It doesn't have to be a box. Your shape can be a peanut, literally. You would just take your surface differential of your peanut, and the electric field might not even be symmetric to the peanut. Maybe the electric field is some weird shape that doesn't have a consistent expression or a consistent relation in orientation with the peanut. You could still use Gauss's law. It just won't be easy. No matter what you do with something that looks like that, it's not going to be easy to integrate because the electric field changes its orientation relative to the surface differential. And because it changes its orientation, you're going to need to know how the electric field varies as a function of the area. And the reason why you would need to know how the electric field varies as a function of the area, it's because you have an area differential. You're integrating with respect to the area. So Gauss's law isn't good for, well, let me rephrase that. You could use Gauss's law for any flux, but if you don't know how to describe the electric field, and if you don't know how to describe the area mathematically, then it'll be like swimming upstream. Where Gauss's law is useful is for those problems when you have some level of symmetry. So let's take a look at our very long line of charge. So this long line of charge, I will just draw it like this. Now, when we say long line of charge, what that means is it is so long that you could essentially treat it as if it is infinitely long. That means any point on the charge is far from the ends. And since any point on the charge is far from the ends, this becomes now a situation in which you have a charge configuration that has cylindrical symmetry because the electric field is uniform. Let me rephrase that, not uniform. Rather, the electric field looks the same no matter where you are on the surface of the cylinder. Or maybe I should say, no matter where you are on a particular surface of the cylinder. Why this is useful now? It's because if we look at the side, so if we're standing on the side, the electric field looks the same no matter where you are on the side. The electric field is still parallel to the area differential. The electric field is constant in magnitude. So no matter where you are on the side of this cylinder, the electric field looks the same. Why that is useful? That means the electric field is constant relative to the area. And I'm going to just copy this to the next page. So the electric field is constant relative to where you are, at least on that side surface. So where you are then, that part of the integral that said we had to integrate the electric field of the side dotted with the surface area of the side, well, because the electric field is constant relative to the area, that means we could pull out the electric field to outside the integral. And actually, before I do that, let me write the alternative form of representing a dot product. So if you look at this, the angle between the electric field and the area vector is constant. The electric field relative to that surface is constant. Since both of those are constant, they come outside of the integral. And you're left with the integral of the differential, but the integral of a differential is just whatever value that differential represents. In this case, the area of the side. So we could avoid a complicated integration by using Gauss's law. And in this situation for the side with cylindrical symmetry, well, we know that the angle between the electric field and the area differential is 0 degrees, which makes this 1. So for a side, not the ends, just the side, that electric flux is just the product of the electric field and the area of the side. And then if we look at the other pieces, because remember on this page, we had 3 pieces. We just did this one. We still have to look at, we still have to look at that one. That's the right cap of the cylinder. And we have to look at the left cap of the cylinder. So let's look at the right and left caps of the cylinder. I'll just take it to another page. This will be the left cap of the cylinder with an area vector that points to the left. Notice on that left cap, we have an electric field that looks like that. So actually there is like no electric flux through that cap because there are no field lines that cross the plane of the left cap. Another way of looking at that is because the electric field on that left end is perpendicular to the area differential, and let me write that as a differential. When we apply Gauss's law in this form, I'll just call this theta L for the angle between the electric field and the area on the left. Well, this angle is 90 degrees. Cosine of 90 is 0. So for that left cap, the result ends up being 0. And the same is true for the right cap. The right cap, the area vector is pointing away. The electric field is also perpendicular to that area differential. And so for that right cap, ER cosine theta R dAr, well, again, this evaluates to 0. This is 0. So when you have a closed surface like we did, you again can break that up into an integral over multiple surfaces as long as you're completely enclosing your volume of space. And because of symmetry, we know that for this long line of charge, the flux through the left end is 0, the flux through the right end is 0, the flux through the side was the product of the electric field and the area of a side, and all that is equal to Q over epsilon naught. So Gauss's law makes calculation of electric flux for something with symmetry almost trivial. And I'll point out that the area of that cylinder is 2 pi r times the length of the cylinder, epsilon naught. So why use Gauss's law? Use Gauss's law to help make problem solving similar for problems in which there is, or simple, I meant, for problems in which there is symmetry in the charge configuration, symmetry in the electric field. Because symmetry in the electric field means that you could find some kind of surface that is symmetric to the electric field. And if you could find a surface that's symmetric to the electric field, then Gauss's law will help you. And if here's a surface that is not symmetric to the electric field, so I wouldn't use Gauss's law for that surface because the electric field looks different based off of where you are on the surface. So definitely recognizing types of surfaces that match the symmetry of an electric field is important. So for me, that's probably the most important conceptual things from the chapter on Gauss's law. And the rest is really applying Gauss's law in different situations. Okay, any questions? Okay, so I see that in the time I've been talking, there's more students who've shown up. Hi, Anthony and Kaylee and Sophie. So I was just going over things. You know, I don't have a particular agenda. My goal is to help you all. And since there's no specific questions at the beginning, I just thought I would use the time to just really emphasize the importance of Gauss's law. It is a tool that is very helpful. And actually, while I'm sharing with you what I've been doing, I do want to go back and mention one more thing about what I just did. So just because it was an important point that I wanted to mention, because students often miss this when they're doing calculations. So I'll do that, and then I saw that Sophie had a question. So Gauss's law, and I will write it, the electric flux through a closed surface is equal to Q enclosed over epsilon naught. So the thing I wanted to emphasize here is, what do we mean by Q enclosed? Well, it's the charge that is contained within the surface. So for this illustration I have here, it would only be this portion of the charge. Nothing outside of that surface would be part of Q enclosed. Q enclosed is what's only held inside the volume that's bounded by the surface. Very important point. Okay, so any questions on that?